So we have the last of the oxygen nucleophiles. We definitely have kind of a goofy reaction in this case. You might remember from previous mistakes that when you see this O3, you should be thinking kind of MCPBA. And if you think MCPBA, you should be thinking about making epoxides from an alkene. Interestingly enough, MCPBA will also react with carbonyl bonds as well. So what we would end up doing is if we take a look at, say, a ketone or an aldehyde, so those are going to be our primary functional groups that we're looking at when we react with these. So our carbonyls need to be ketones or aldehydes. How do you spell aldehydes? There we go. What we end up seeing is that an oxygen gets inserted between the carbon and carbonyl bond. So what ends up happening is we drop an oxygen right in between there. Very odd result for this reaction. So we'll just kind of go through and come up with a rough mechanism for this. When we're looking at our epoxide or our reagent, we do have this big old long deal, and a couple interesting things can come out of this. Number one, it's acidic, so we can pick up a hydrogen. And we'll probably run it under slightly acidic conditions as well. The result is that we now have our protonated, what did I use? I used the lone pair. We have our protonated carbonyl, which is resonance stabilized. Whoa, that was ugly looking. Let's try and draw that one again. Resonance stabilized in such a way that we can end up putting a positive charge on our carbon. So what we've done is made our electrophile more electrophilic, kind of a sweet system. The oxygen from our peroxy structure then can do a nucleophilic attack on our nice electrophile, and we end up with this lovely looking junk pile, if you will. Well, I guess we shouldn't be that mean about it. It's actually kind of a neat reaction. It's just ugly that it has to happen to us. And we've got our hydrogen out there. Still have our peroxy bond. Okay. Now we've got an interesting dilemma. We still have the weak oxygen-oxygen bond that still wants to push electron density towards our carbonyl. Okay. The issue with that, could even go over here, is pick that up, is that that oxygen is then missing electrons. So what our carbon structure does, and this is where it gets weird, is that we decide to take this bond and the electrons in that bond, and we slide those over towards that oxygen. Okay? So that supports the breaking of that oxygen-oxygen bond. If we pushed our arrows all the way around, and in all honesty, I don't know if we actually do something this massively cyclic, we can rotate and reform our pi bond. So let's redraw this with our product. I'm going to draw in purple for most of it. I'm going to keep kind of the general skeleton. So that's where that empty space is where we would have had our bond. There's our oxygen, our carbonyl oxygen. There's our other oxygen from our peroxy, and now we have that last bond. And you may look at that and go, oh my gosh, that looks ugly, and I agree with you. So let's go ahead and try and clean that up a little bit. So we've got 1, 2, 3, 4, 5, 6, 7 atoms within a ring. So if we attempt to draw this, probably do a horrible job of it. Already starting to draw it wrong. Let's see, 1, 2, 3, 4, 5, 6, 7. I think I got them in there. We still have our carbonyl, and one of those atoms is an oxygen. Come on, eraser. And we end up with this massive looking structure, and we would also have the carboxylic acid floating around now in solution. So this reaction, doing some crazy stuff within it, is what's known as the Baeyer-Villiger reaction. Our epoxide reacts with our carbonyl compound and inserts an oxygen into it. The main reason it does that is in this structure here, we have that weak oxygen-oxygen bond, and we need to somehow facilitate or stabilize our positive oxygen. So we end up seeing this weird carbon shift to stabilize that. Okay? Within that shift, it turns out that we see some things shift more frequently than others. It's got to be something that's attached to our carbonyl carbon. So you'll notice that in this case we really only had two options, and both those options were the same thing. So what we're looking at, again, is which of those groups would move. Well, in this case they're the same, so we don't care. What we're getting is what's known as a migration. So we could look at a migratory characteristic or attribute. This is kind of up in the air. We don't have a really good explanation for this. But in general, the more stable the carbocation, so a more stable carbocation, or stable cation, is what shifts. Okay, and I know that's kind of a tricky concept. So what we're saying is, if we went through and changed this structure, okay, and I go back to that starting material, and now we can ignore the mechanism, and I put in an extra carbon on that structure, so we add an extra CH3. Now when we go through and get to our intermediate stage, you'll notice that we'd have another carbon there. So between so much stuff to look at, we've got this carbon versus this carbon. Which of those would form a more stable carbocation? Well, the one on the left would be depending on how you want to look at it, a tertiary or secondary carbocation. The one on the right is a primary or secondary carbocation. Well, the tertiary is more stable, so we would expect the tertiary to shift, which means that the oxygen inserts itself on this side, which means when we go through to look at our final product, we would expect that methyl group to be right here. Okay, kind of odd, but that's just the way this reaction happens to work, and that's where we'd see our CH3. Okay, so be aware of it. I gotta admit, I probably won't test you on it, and I don't think any of your future tests will test you on it either. It's just kind of an interesting reaction. We can see oxygen as another nucleophile with our carbonyls. So here's your choice. We got a new problem for you. This is going to be one of the ones for you to go through and solve, and we'll talk about this one in class. So if you want an answer, you gotta show up to class. Lucky you. What we're now going to move into is nitrogen as a nucleophile. It's a little bit different from our oxygen, not hugely, but we do see enough of a difference that our chemistry looks a little bit odd and different, and everybody panics and thinks it's something crazy different. So, as a kind of rule, when we're trying to decide between different chemistries, we should evaluate our differences. Oxygen versus nitrogen. Well, we've seen oxygen, so what does a nitrogen nucleophile do? How does it interact? Well, when we're looking for our differences, there's two places that we should focus on. We should look at size, and we should look at electronegativity. To really determine those, our size, we can go to our periodic table, or our PT, and we would see that both oxygen and nitrogen are in the same row. And as I've said several times in class, when we're looking within a row, at least in organic chemistry, we kind of ignore size. We're putting electrons into the same energy level orbital. Roughly, to a first approximation, our size does not change. So there is no difference between size. If we now move to electronegativity, this one's a little bit crazy. Oxygen is more electronegative. Okay, and this is where we're going to have to be very careful with our definitions. We're looking at electronegative. If it is more electronegative, okay, that's not the same as saying it's more negative. Those are two different statements. So if we look at a nitrogen atom and an oxygen atom, okay, and they're kind of stable neutral states, I don't really care what's attached to them, okay, they both have lone pairs. One of the tendencies is to say oxygen has two lone pairs so it can react twice. Not the case. When we're looking at the first reaction, we can only react a single pair of electrons at a given instant. So when we're trying to decide a difference here, focus on they both have electrons, and now we move on. Oxygen is more electronegative. That means that it is willing to hold its bonding electrons. So if we now go through and take a look at the likelihood of taking one of those lone pairs on each of those atoms, oxygen becomes less likely to share them because it wants its electrons. Well, if oxygen is less likely to share them, that means our nitrogen is more nucleophilic and more, of course, if it's nucleophilic, it's also basic. So it's those characteristics that are really going to play a role when we're looking at what happens when we add a nitrogen as a nucleophile instead of oxygen. What does that mean when we go through and look at our carbonyl? Well, with our carbonyl, what happened when we added an oxygen, say an alcohol? Well, our result was that it went all the way through to an acetal. And we ended up adding two equivalents of our alcohol. Why do we have to add two equivalents? Well, we had to add two equivalents because oxygen's a crappy nucleophile. Okay, so we put one on and it's kind of happy at that. Can't really do much more than that. If we switch this up instead to now a nitrogen being a much better nucleophile, so long as we've got at least a hydrogen here, the nitrogen will go through and do a very similar reaction, except now that second lone pair can completely swap out. And so the net result is that we can convert our carbonyl into this new nitrogen species, the nitrogen equivalent of a carbonyl. Okay? And that's only because nitrogen is more nucleophilic, so we don't have to add it twice. It's already nucleophilic once it's attached, so it reacts a second time. Kind of a sweet situation. If you want to consider things sweet like that. Okay? So, what the? Stupid. Go away. So let's go ahead and move to the next one. Here you're going to end up doing a mechanism, and yes, I will ask you to do this in class. In groups of roughly 2 or 3, work out a mechanism to explain the following reaction. For those of you going into the tutoring center to get help, I really appreciate that you're going in to get help. You better understand every single step of this mechanism. Okay? This isn't just I need an answer, so I'm going to write it down on the board and now I feel happy. That is not the point of these quizzes. The point of the quiz is to go through and actually practice the material on your own. If you get it wrong, who gives a crap? Right? It's practice. It's only when you get to the exam that you need to be worried about getting it wrong. And if you are worrying about getting it wrong now, you won't learn it. Okay, so go through and try and come up with what you think is going to work as a mechanism to go from the carbonyl to this new nitrogen structure. Okay? When you get into class, when we get to this question, I will ask you to go through and work within some groups and come up with an idea of what you think the mechanism is. Okay? Please do not pull at your textbook or any other references. Look at what you think is going to happen and work from there, and only from there. Okay? That's all I'm going to say. Things that you'll want to address is what conditions did you draw your mechanism? Were they acidic or basic? Did we add a catalyst? Why? Why not? Okay, so those are things to consider once you've actually got your mechanism drawn up. That said, let's go ahead and take a look at this. We said nitrogen was a stronger nucleophile than oxygen, and it's also a stronger base, which makes things a little bit tricky. If we do decide to go through and add an acid catalyst, if nitrogen is a stronger base, what we might expect for our very first step of this reaction is the acid to react with the nitrogen to give us this species. Well, that's a bit crappy, because if we take a look at the product, that product is not a nucleophile. And if it's not a nucleophile, we can't get it to attack the carbonyl carbon, which is ultimately what it needs to do. Remember, this is an equilibrium. We have not added an excess of acid, it's just a small catalytic amount. If we instead look at the other option for where that hydrogen can go, we have the carbonyl, and we could go through and say that that attacks at our pi bond, which is resonance stabilized. That resonance stabilization increases the likelihood of the hydrogen going to that carbonyl carbon. We would still expect there to be a strong favoring, whoops, we fix our equilibrium arrow, of our starting material. Okay. Much the same situation with, or not quite the same situation that we've got with our nitrogen. So why would an acid catalyst go after the carbonyl? The answer to that question has to really do with all of the individual steps of the mechanism. When you go through and evaluate your mechanism, you should notice that at every single one of your steps, they are equilibrium steps until you do your final step, which is the elimination. That elimination is not easily reversible, particularly if we're in a situation that has a lot of the amine and virtually no water. Under those circumstances, it is a non-reversible step. So if we propagate our reaction all the way through, we may generate a very small amount of the active electrophile, okay, after the catalyst is added. But that small amount is constantly being depleted by the subsequent reactions, which means eventually we can end up converting all of the carbonyl across to our nitrogen-containing compound. Okay? So, be aware we can see these other kind of weird side reactions occur, but if they don't produce anything for us, what we need to do is look at another situation and say, hey, does that work? Okay, what happens if I propagate this further along? And yes, you might very well find that you've got to propagate 6 or 7 steps down the road to find out that that method did not work and you double all the way back. That's fine. It's homework. You have to go through those failures. If you do not fail, you will not succeed. So please, spend the time to fail with your experiments and learn from why you made those mistakes. So, more practice problems coming along with this. Some extra terms to be aware of. This reference to an imine, it's also known as a Schiff base. We actually just saw the structure of that. Your imine is the nitrogen equivalent of the carbonyl. The enamine, if we look at that name, sounds a little bit weird, but what we're referencing in that case is this guy. In this case, we have an alkene and we have an amine. So we have an enamine. Enamine. A whole bunch of problems to go through and work and kind of deal with what happens within each of these stages. Be aware, some of these will go through and give you an amine, some of them will give you an enamine. It's all going to depend on the stability of intermediates as you've got them drawn out. As you go through and do your work, your previous mechanisms, hopefully you'll be able to see why you would get one over the other. And yes, it's going to come down to stability of each of those individual species. Hydrogen nucleophiles. We very rarely see hydrogen as a nucleophile, and that is largely because hydrogen is very mild electronegativity, so it doesn't want electrons, or it won't take electrons from something else. And not only that, but once it has taken electrons, it's now effectively a point charge. We have a very, very tiny atom holding on to electrons or negative charge. That tiny charge makes it horribly unstable, which is why it needs special conditions to go through and stabilize it. Okay? So, how can we get hydrogen as a nucleophile? Well, as we talked about within the last section, we've got two common reagents, lithium aluminum hydride and sodium borohydride. And I'll draw those out, and actually I'll draw them out right here. What we're looking at in both those circumstances is that we have our metal with our hydrides on the outside of it. The metal in this case is both aluminum and boron. Both of those atoms are happy with just 6 electrons around them, which means one of those hydrides, at least to start with, is actually holding on to that negative charge. So when we look at the reactivity, we're really seeing a negative on our hydride, and we're seeing a positive on the metal. When we go through and run our reaction, we look at our carbonyl, and we say our carbonyl has a positive on our carbon and a negative on our oxygen. What do? Match them up. Match the metal to the negative and the hydride to the carbon, and we've now done effectively the first step of the reaction. And our hydride has attacked the electrophilic carbon, and we've well on our way to forming our alcohol. In a subsequent acid-base step, we can use methanol in the case of sodium borohydride, or water in the case of lithium aluminum hydride, to supply that extra hydrogen to protonate the oxygen and kick off the metal hydride remains. So we've gone through and done our full substitution. So as a quick summary again, what we're effectively looking at is our H- attacking is a nucleophilic attack, and we end up with our result. So really these reagents are supplying H- as a very strong nucleophile. Okay. One of the questions that may have popped up in our homework was this new reagent, which typically gets abbreviated as DIBOL, or diisobutyl aluminum hydride. So before we even look at that reagent, we've got a couple problems again for you to go through and work. We got 4 questions. You're looking at roughly 2 minutes a question. Yeah, you should go through and time yourself, or you will be timed in class, which is fine with me as well. Okay. You'll notice that last one becomes a little bit trickier because we've involved spectroscopy. If you're weak with spectroscopy, review it. It'll help you out to answering that question. So, supercarbonyls. What's happening with these? When we first brought this up, we were really just focused on aldehydes and ketones. And in the case of our aldehydes and ketones, our R group was a hydrogen for an aldehyde and was some kind of carbon if it was a ketone. If we change this around and actually make that R group a chloride, we now have what's referred to as an acyl chloride. If the R group is some oxygen, which is then connected to some carbon in sequence of hydrogens, we're looking at an ester. If that R group is an OH, we have a carboxylic acid. These carbonyls are special because it changes the chemistry of our electrophilic carbon. So we have to watch out for that change in chemistry. The chloride makes it much more reactive in that the chlorine is electron withdrawing and our carbonyl carbon becomes much more positive. So we get a bigger positive coming out of that. in both the case of the ester and the carboxylic acids, we actually get a smaller positive. So I'm not quite sure how to do this. Let's give it a shot. So we get standard positive. That's still kind of tiny. Standard positive for our aldehydes and ketones. We get a massive positive for our acyl chlorides, and we actually get a smaller positive for our esters and carboxylic acids. Okay? And that's because in the case of the ester and the carboxylic acid, there is resonance stabilization. That resonance stabilization minimizes the positive charge and reduces the overall reactivity of that functional group. And when we brought these up, we were really looking at our borohydride and our lithium aluminum hydride. Well, the borohydride, we said, didn't react. Okay? Just can't quite deal with it, freaks out, we don't have to worry about it. It just dealt with the aldehydes and ketones. The lithium aluminum hydride will react with all three of these species and fully reduce. Okay, so we get no reaction, we get full reduction, which means we go all the way down to our primary alcohol. And then dibol. So dibol is an interesting one, which again we haven't quite looked at it yet, but if you've reviewed the material very carefully, you might have noticed that what dibol will end up doing is it will actually stop after one reductive step. Okay? And that really has to do with the characteristics of it. Okay? We'll look at that in just a second when we look at its structure. So there's our structure. Why is it so drastically different from sodium borohydride and lithium aluminum hydride? Well, if we look at the hydrides supplied in both our borohydride and our lithium aluminum hydride, we have 4 hydrides, which means we've got a lot of turnover ability within both of those reagents. So lots of hydrides come flying out of this. When we look at the dibol, we really only have 1 hydride. Okay? The next aspect of this that is interesting is that when we look at the aluminum in our dibol, we have only 3 groups. Okay, well, what does that 3 groups mean? That means the aluminum is happy as is, which means that hydrogen is actually a pretty normal hydrogen. It is still a metal, non-metal bond, but we aren't looking at the wicked strong nucleophile that's being pumped out by the lithium aluminum hydride and the borohydride, because in those cases they've exceeded their octet. They're trying to get rid of that hydride. Dibol, it's kind of okay. There's no real reason to ditch that hydride. Okay? So that's kind of our big difference here. How does that end up translating into our reaction? Well, the net result is that our hydride now becomes a much weaker nucleophile. Okay? Not to the extent that it doesn't react, but that it's no longer the reactive species within this molecule. What do I mean by that? Well, aluminum still is sp2 hybridized, which means it still has an empty p orbital. Well, what can we put into an empty p orbital? We can put electrons. And that's really our key characteristic for this difference, is that when we look at the mechanism for dibol, our lone pairs, let's see, sorry, I'm going all over the place. When we look at our dibol, the mechanism is that our carbonyl attacks the aluminum first. Very odd. That oxygen actually becomes a nucleophile. That coordination is what then sets our oxygen and our carbon off on the path to actually forming our final product. I think I drew that right for our isobutyls. Oops. Oh no, shoot, I did have that right. There are isobutyls. So that oxygen now becomes positively charged, so it can draw electron density away from the carbon. But now what charge does the carbon become? Well, positively charged. What's the net result of that positive charged carbon? It's now seeking out electrons. Where are their electrons? Oh, look at that. That hydride from our aluminum can now shuttle across a set or a single hydrogen, and we can end up with our now reduced structure that we can then follow up with our H2O, okay, or H3O, something to just go ahead and hydrolyze off the aluminum, and we have our single reduction. So it's interesting. We're still supplying a hydride, it's just being supplied at a different point. The lithium aluminum hydride, if we go through and look at its reagent down below, what we said happened in this circumstance was that the hydride attacked the carbonyl carbon, okay, which then gave us the result of our carbon with the extra hydrogen, our oxygen with a negative charge that can then coordinate to our aluminum. Okay? So we end up with the same kind of coordination. It's just a question of how and when it occurs. In the case of our lithium aluminum hydride or our borohydride, hydride attacks. In the case of dibol, the carbonyl attacks. So why does that matter? Well, that's going to matter because that's going to change our end results of when we're looking at the reactivity. So dibol, because it only supplies one hydrogen or one hydride and is in a much more stable state, we can measure out the dibol relatively easily, whereas the lithium aluminum hydride and the borohydride, as soon as they hit atmospheric pressure or really atmospheric water, they start to react, and we lose some of those reaction equivalents, which means we have to add an excess in. With the dibol, because it's relatively stable, we aren't really concerned about the loss of those hydrides, so we can measure out an exact amount, okay, to get a very perfect 1-to-1 ratio. That allows us to go through and do single reductions, okay, which is nice. So we can move from an acyl chloride to an aldehyde. If we want to take it to an alcohol, we can add a second equivalent of the dibol. We can do the same thing with our esters and our carboxylic acids. How does this end up working out so much differently? Well, if we compare the reactivity of, say, an ester functional group to an aldehyde, when we look at our dibol, what we're concerned about is the oxygen coming in and doing the attack, which means the ester oxygen is actually more nucleophilic due to that resonance. Which means I can go between an ester to an aldehyde and I can stop at the aldehyde because the aldehyde is actually less reactive than the ester. Right? Because the aldehyde isn't reacting as an electrophile. It needs to react as a nucleophile. But the ester is a stronger nucleophile. So we get, because the mechanism changes, we can actually get better control over how we reduce individual functional groups. So kind of a neat reagent as far as that goes. You may or may not see that pop up on many of your tests. So, hydrogen nucleophile extras, we got pretty much 4 problems here. Most of these are looking at dibol, so take a stab at them and see what you can go through and do. You'll notice that I did add some kind of trickier questions in here. We aren't looking at just carbonyl compounds. Okay, remember that the imine is pretty much the same thing as a carbonyl compound. It just has slightly different characteristics. Okay? So go through and tackle these and see what you can come up with as far as the reactions go, as you get slightly different chemistries happening out of it. And when you got questions, you can ask them in class. Another synthesis question. This is really looking at our carbon nucleophiles. So we got kind of a fun structure here. The final product in this case is an isoprene derivative. In fact, a highly active isoprene derivative because of that carbonyl. Very common biomolecule. I don't know if that quite got recorded. So that unit is what's known as an isoprene. When you move into biochemistry, take a look out for that. You'll find that a lot of molecules contain those. Cholesterol. Here, let's just change that around because I don't know how to spell cholesterol. Steroids. Steroids tend to have lots of isoprenes. Beta-carotene. So your carotenes have isoprene units. There's a lot of important biomolecules that carry these. This is a bit of a challenging reaction. If we look at this, you should be able to do this one based on information that you already know. So nothing in the subsequent slides, I think, is necessary to get you to go through and solve this one. It takes a little bit, but you should be able to go through and pick it up. Okay. Like I said, a little bit of a challenge, but you should be able to go through and do it. Within our carbon nucleophiles, there are three common ones that we've already seen. You've seen the acetylide, you've seen the Grignard, and what I'm going to call the Grignard-ish, and then we've also seen the cyanide. A lot of people seem to be forgetting what's going on with the cyanide, so let's draw out a Lewis structure for that. And everybody seems to forget our rules, so let's go all the way back through it. Carbon has 4 valence electrons. Nitrogen comes in with 5. We have a negative charge, so we'll add 1 more electron. We need a total of 10 electrons going into the structure. Carbon's our center atom. Nitrogen, put our electrons around the most electronegative first, and then around our least electronegative. We've got our 10 electrons. We can go through and erase, drop in our pi bond, or sorry, a single bond. Nitrogen has its octet. Carbon is missing its octet. So we'll go through and shift a pair of electrons in to form a double bond. Nitrogen still has its octet. Carbon is still missing its octet, so we will shift another pair of electrons into a triple bond, and we now have a reasonable electron dot structure. Final step is to calculate formal charge. Formal charge is equal to our valence electrons minus bonds minus non-bond electrons. So in the case of our nitrogen, nitrogen comes in with 5, minus 3 bonds, we're down to 2, minus non-bonding electrons, we're down to 0. Nitrogen is neutral, which necessarily means the carbon's negative. So let's go ahead and check that. Carbon comes in with 4 valence electrons, minus the number of bonds. There's 3 bonds, so 4 minus 3 gets us 1, minus the non-bonding electrons. There are 2. 1 minus 2 gets us a negative 1 charge. Hey, look at that, a negative carbon. There's our carbon nucleophile. Okay, so what we're concerned about within our carbon nucleophiles is that we ultimately have a negative carbon. So if we evaluate something about our common traits within these, the acetylide and the cyanide are very, very similar, and that the carbons that we're looking at for both of those, so we call this A and C, our acetylide and cyanide are both looking at sp carbons. And we go through and run those reactions, which also kind of necessarily means that we introduce a triple bond in the course of our reaction. The Grignard is different. Okay, the Grignard and the ish are different in that we can really run with pretty much any hybridization, so all carbons. They're also a little bit higher on the reactivity scale because we don't have that hybridization stabilization. The ish reaction might look a little bit foreign, like, oh, we didn't talk about that. We didn't need to talk about that. Magnesium is a metal which inserts itself between the carbon and the bromine. Lithium is a metal which can insert itself between the carbon and the bromine. So we get the same result. The only thing that's slightly different about the ish reaction is that we actually need 2 equivalents of the lithium. So here's a nice little random question. Why do you need 2 equivalents of the lithium where we only need 1 equivalent of the magnesium? I'll let you think about that for 5 seconds. We take a look at our Lewis structures. Magnesium has 2 electrons, lithium has 1. To go through and make the lithium-carbon bond, we need 2 lithiums because we need 2 electrons to make that bond. Okay? But you get pretty much the same reactivity coming out of that. The lithium-carbon reagents are a little bit more reactive just because the lithium is smaller. Okay? So we got to watch out for those reagents a little bit more so than we do the Grignards. So those are our common nucleophiles. We can pretty much react them however we like. The acetylides and the cyanides work really well in substitution reactions. So we'll see those pop up with our substitutions. The Grignards, not quite as common with our substitutions. We're really looking at those reacting with carbonyl compounds. So we're doing really kind of an addition in those cases. That said, oh, mosquito. Cyanide and acetylide will also work in addition reactions as well. Okay, so the Grignard is really just a weaker version of this reagent. And I need to pause here a sec. Okay, we're back. So, moving on. If we look at our acetylide and cyanide, these are both kind of cool reactions, as we already kind of alluded to, because they have the potential for secondary chemistry. If we went through and reacted our carbonyl with our acetylide, make that bond a little bit shorter, we could end up with an alcohol and our triple bond. And then whatever R group we had attached off of that. That gives us access to now both the alcohol chemistry that we would get when we react carbonyls, but we also have this pi bond chemistry. So everything that we remembered from our alkyne chapter can now pop back in with the alkyne functional group, which is kind of fun as far as synthesis goes. If we go through and look at our cyanide group, this one's a little bit on the newer end. We can put in our alcohol, and we now have our carbon-nitrogen triple bond. Also, interesting chemistry there. We actually already alluded to some of that when we looked at nitrogen as a nucleophile. We could go through and hydrolyze this by adding H+, and H2O, and we can convert that triple bond all the way down to a carboxylic acid. So again, depending on what we were looking for, that might have been a useful synthesis step. Right? And that happens because the pairs on our electrons can come out, react with the hydrogen, increase the electrophilicity of our carbon, water can attack, and that happens multiple times. This is one that if you would like me to, I can draw out the mechanism for you in class, though I will make you work for it. Okay? So we just get some extra chemistry coming out of these. That's all that's kind of nice about mentioning them. Really only mentioning them as a review because we've seen them show up before. So, carbon nucleophile questions. We got 3 more problems here. Formatted them all in slightly different fashion to kind of make it a little bit more interesting for you to play around with and see what you can come up with. Last reaction of chapter 21. Look at that, we're almost done. It's known as the Wittig reagent. Okay, when we talked about Grignard, we said forming carbon nucleophiles was an awesome thing to do, and it was so important that Grignard received a Nobel Prize. Well, Wittig was able to do something similar. He generated a carbon nucleophile as well, but his was even more interesting because his carbon nucleophile resulted in or a maintenance of an alkene functional group. So we actually keep some chemistry with the Wittig reagent. He received a Nobel Prize in the 1960s. So we've got a lot of connections going on within this. So this is a very tricky reaction to deal with. So what I want you to do is take a minute and try and figure out what appeared to have happened in the above reaction. So look at the beginning and end, right, from here to here. And because I have no faith that you're going to go ahead and pause the video now, I'm going to go ahead and be quiet for a good 20 seconds. So one of the things you may have noticed is we're looking for those carbon connections. How did those go through and change in the course of the reaction? And that may not be easy to pick up, but it is there. If we go through and highlight the carbons that we started with, these 3 carbons and these 4 carbons, you might see that those 4 carbons are right there, and that our initial 3 are here. The result of the Wittig reaction is that we take our carbon and we connect it to our carbonyl carbon, and we pretty much swap out carbon for oxygen, or oxygen for carbon, and we generate our new pi bond connecting 2 carbons. Fascinating reaction, and how we figured this out I don't really know, but it's kind of neat. So to go through and do this, of course, we're going to have to use some kind of crazy reagents to figure out what's going on. So usually occurs in 3 steps, and it depends how the question is phrased, because you might be given the carbonyl as your starting material. So I've got it broken down in the process that goes from our alkyl halide to form our reactive carbon nucleophile, which we can then react with our carbonyl compound. So in step 1, we react our alkyl bromide. Kind of neat, because that's similar to what we did for our Grignard reactions. We react our alkyl bromide with triphenylphosphine. Okay, so that's phosphorus with 3 phenyl groups. As you might guess, that is a massively sterically hindered structure. Okay, interesting structure. We then react that species, or that product of that reaction, with butyl lithium. Butyl lithium we've seen before. That was our Grignard-ish reagent. Kind of interesting, because we don't see that butyl showing up in this product, which is kind of puzzling, but we'll look at that in a little bit. And then in step 3, we end up reacting our now superactive carbon nucleophile with our electrophilic carbon to get us to our final product. So I'm going to give you another 20 seconds here to think about the mechanism / reaction guesses. So look at step 1, what's the nucleophile, what's the electrophile? In step 2, what is the structure of butyl lithium? What can it do, particularly with respect to the product of step 1? This is the formation of the Ylide, by the way, which is your Wittig reagent. And then for step 3, what is your nucleophile and what is your electrophile? Here's your 20 seconds. Have fun. That gave you 30 seconds. So you got it all figured out. So, step 1, on the way to the Ylide. What is the nucleophile and what is the electrophile? So be considering what type of mechanism is most likely and why. Ideally you wouldn't see the conclusions right away, but hey, sometimes you get a little preview snapshot of what's happening. So, we look at this reagent. We want to identify our nucleophiles and our electrophiles. So we want to look for negatives and positives. Because you've already been thinking about this, hopefully what you see is that with the alkyl halide, we really only end up with an electrophile. Okay, and that's because really the halogen can only act as a good leaving group, and that really leaves that carbon as partially positive. Well, if that's the chemistry we see coming from our alkyl halide, what happens over with the other structure? Well, the other structure must be a nucleophile. Turns out that that phosphorus, in particular the lone pair, is our nucleophile. Interesting little structure there. So what's going to end up happening is that that nucleophile then has to react with that electrophile, and we end up with our phosphonium structure. Okay, so now the question becomes is what mechanism was most likely to occur? Well, if we look at the overall reaction, what happened? Hopefully you can pick out that we've done a substitution reaction. We now want to piece together, do we have SN1 or SN2? So we got a couple ways we could strike at this one. Most people would probably jump to the nucleophile. So we take a look at that nucleophile, and we got a massive phosphorus structure. I mean, that thing is just stupidly big. So we would probably be pushing this towards a weak nucleophile. And I don't blame you with that thought process. Unfortunately, phosphorus is so much larger than our standard atoms that we're used to working with that really that phosphorus does not act very well as a, well, I'm not even quite sure where I was going with that one, to be honest. Phosphorus is a tricky nucleophile. Let's leave it at that. So let's avoid the nucleophile topic and move on to the next piece of information we've got, the substrate. When we look at our substrate, what type of substrate do we have? Well, it's a primary substrate. And primary is only favored in one type of mechanism. It is only favored in the SN2. So this has to happen via a backside attack, and we get this SN2 result. Okay, what does that mean for us? Well, that means that our reaction is going to work best with primary alkyl halides because they are less sterically hindered. We try to jump through to a tertiary, we've got this massively bulky phosphorus structure that's just not going to be able to get in and kick out a leaving group out of the tertiary carbon. Okay? So what we're really hoping for here is a primary alkyl halide, and if we've got them, we can run with a secondary, but for the most part we tend to stick with those primary alkyl structures, or alkyl halides, just because we can get this reaction to work much more effectively with those. The next part of this that's kind of important is this then primes this structure is now primed to pick up a negative charge on our carbon. And what do I mean by that? Well, we have a positively charged phosphorus. Phosphorus doesn't want to be positively charged. It needs electrons to stabilize it, which means the carbon that's attached to it is now going to start to say, hey, I can help out this phosphorus if I can just ditch a hydrogen ion. And that's really what happens in our next step. So what we're concerned about is that one of these little happy little hydrogens that are attached to that hydrogen structure, or that carbon structure, need to get pulled off so that that carbon can pick up that electron density and become that strong nucleophile. So we've really super primed our carbon and getting it really ready to go so that it can become negatively charged. When we move to the next step, what we're really concerned about is looking at these pieces. Okay? We could go through and say that we've got a reasonable leaving group as a possibility, because I mean we started with it, might as well end with it. So we could potentially see that this negatively charged carbon from our butyl lithium come in and do a backside attack to kick it out. The issue with this is that those phosphorus structures or the phenyl groups off of our phosphorus are now also kind of blocking that carbon, okay, making it sterically very difficult to get access to. If it is difficult to get access to, then our butyl lithium probably will not act as a nucleophile, even though that's how we might have initially predicted it. Okay? So what ends up happening is when we look at our reactivity, I can spell nucleophile, our nucleophile activity is not really there. What we see instead is the base characteristics of our butyl lithium. And what it will end up doing is tugging at one of those hydrogens that's attached to our carbon. So the negative carbon comes in and pulls at one of those hydrogens and takes those electrons onto our carbon. Okay? The result of that acid-base reaction, we draw this out, we've got our nucleophile option, I forgot how I parsed this one, and we've got our acid-base option. Okay, and we just addressed some of the issues with our nucleophile option. We have a lot of steric bulk. Okay, so the sterics are going to slow down that substitution reaction. Taking a step further, the phosphorus isn't the greatest leaving group. I mean, it's not horrible, but its leaving group ability is not all that great. That's why it could actually attack the phosphorus or the carbon to begin with. If we look at the acid-base reaction, we might be going, oh my gosh, this is even worse. We're generating negatively charged species. We've got this negative and the positive, except what happens if you've got a negative and a positive? We can generate a double bond. There is resonance stabilization of the acid-base reaction. That resonance stabilization is going to be the prime driver for why we see butyl lithium act as a base in this circumstance and not as a nucleophile. So the result is that we see our carbon build this negative charge. Between the two resonance structures shown, we might go through and say, well, the one on the right is the best. Turns out it's not the greatest, and the reasoning behind it isn't super obvious for most people to pick up, but what we've got is this phosphorus is in a second or the third energy level, which means its outer shell is probably something like this, whereas our carbon is probably in something like this. So trying to get the electrons to share across isn't quite as easy to do. We get minimal p orbital overlap. I'll get rid of the Ly. Minimal p orbital overlap, which means weak pi bonds. Okay, so we really do see kind of a predominance of this negatively charged species, and that species is really known as the Ylide, okay, which is kind of fun to say. Go ahead, I'll give you a couple seconds here where you can just go through and say that to yourself out loud. You know, scare some of the people next to you. I mean, I'm talking through my office. You might as well scare some people that you're listening to the video with. So all together now on 3, 2, 1, Ylide. Okay, do it again. 2, 1. Okay, hopefully you like that. Ylides. So we now have a carbon nucleophile. Pretty freaking sweet. Okay, that resonance stabilization is really what drives this reaction, and we now have a carbon nucleophile. Awesomeness. Now we've got this nucleophilic carbon with a slight caveat with it. Okay, and it's really going to come back to the phosphorus chemistry. We've now linked the carbon to the phosphorus. Those are nonpolar covalent bonds. It's not the easiest bond to deal with and break apart. Okay, so there is some debate into how this mechanism actually occurs, and depending on certain conditions, which is why we get a debate, we end up with different products coming out of this, or slightly different products. Okay, so we got to be a little bit careful with how we look at this mechanism. But ultimately, everything that one thing we can all agree on is that that negative carbon interacts with the positive electrophilic carbon of our nucleus, or of our carbonyl. Okay, so this partially positive carbon interacts with our negatively charged Ylide. So that goes through and attacks that position, which then, of course, breaks open the oxygen. Okay, so our oxygen then becomes negatively charged. But if we look at the geometries of what's happening in that state, is that phosphorus, that positively charged phosphorus, and that negatively charged oxygen are darn close to each other. So close that they actually form a bond. The real question with this debate is a question of whether it forms that bond at the exact same instant that our carbonyl was attacked, or does it happen in 2 steps. We don't really know for sure, and our results never seem to help us out. Okay, so we don't know if this is a step 1 followed by a step 2 in blue, or if they all happen in one big fell swoop. But ultimately we do have to end up with this cyclobutane looking structure. Okay, this is where we then advance forward from. Okay, the phosphorus, which we saw when we dealt with the phosphorus tribromide, if you remember your PBr3, so we'll draw that in real quickly here. We looked at our alcohol and we reacted PBr3. What happened is we had our oxygen attack, we kicked out a bromine, and we ended up with this species, which we said was an awesome leaving group. So the bromide could then come in and kick that out. So what ends up happening in that case is the oxygen does coordinate to the phosphorus, and we end up with this kind of phosphorus oxide compound. That phosphorus oxide is actually a pretty strong bond, and that's kind of what's driving this next situation. We see a swinging of electrons. The oxygen says, you know what, I'd rather share with phosphorus than I would with carbon, so it takes the electrons from carbon, makes a pi bond between the phosphorus and the oxygen. Phosphorus now says, well, heck, since I've got my electrons, I'm going to give them back to carbon. Okay? And the net result is that we see an alkene form, or really 2 alkenes form. We form or 2 pi bonds. We get the alkene pi bond, and we get the phosphorus oxide pi bond. Okay, the next question here is this the product? Okay, so if you take a look at this product, or is this the only product, I guess we should really be saying, is there more than one type of product that could come out of this? And as a big hint, I'll tell you it really has to do with this double bond. All right, and I'll give you another couple seconds here to think about it. I'll give you another big clue. It has to do with this carbon. Another couple seconds. It has to do with this carbon. What type of pi bond did we just make? We have the trans or E product that came out of this. Did we have to form the E product? Turns out no. We could have also formed the Z product. The Wittig reaction generates both isomers in this reaction, so we have to be aware of that. When we do our elimination, we will, or when we do the Wittig reagent, that we will end up with both E and Z isomers coming out of our reactions. Okay? Depending on certain reaction conditions, we might see a favoring for one over the other, but that's ultimately into mechanistic detail that we really aren't going to look at. Okay? So we really do see a formation of both. Okay? Tricky, tricky. So results, our carbonyl as an end result can be converted to an alkene with carbon chain lengthening. So we get that carbon nucleophile, and we can make our structure much larger with an addition of multiple carbons. So it's kind of a neat result. We also get a mixture of E and Z isomers with our elimination product. So when you're looking at a problem on how to make an alkene, one possibility is that we are looking at going through a Wittig reaction. Okay, so add this to your repertoire of possible reagents. So here's some Wittig questions. You noticed, or you may notice, that I've got these formatted in slightly different situations all the way through it. Think about each of them, how they would go through in process. The very last one there are 2 Wittig methods to go through and make that final product. Okay? When you find those 2, decide which of those 2 is the better mechanism. Okay? Hopefully you can find both of them without too much difficulty. Last but not least, we now have a complete shuffleophagus for synthesis reactions. So this pretty much summarizes everything within these last sequence of slides, both carbon nucleophiles, nitrogen nucleophiles, all of that fun stuff. Okay? Take your best stab at them, and we will take a look at these in theory. Hopefully we'll see them on Wednesday when we meet in class again. Until then, have a good night, and if you got questions, feel free to send me an email.